Yeah, welcome everyone to our today's MCQST Colloquium. So it's my great pleasure to announce our speaker, Vladan Vuletic from MIT. So Professor Vuletic is an expert in laser cooling and trapping and is interested in studying quantum entanglement, quantum optics, quantum information processing of few to many particles. So with so much quantum in all the research topics, I mean, it's an optimal fit for our MCQST. So Vladan also has a long-standing connection to Munich. He has studied at LMU and has graduated under the supervision of Ted Henge. And after that, he went for his postdoc to Stanford to work with Stephen Chu. Also at Stanford, he was appointed already as assistant professor, but a couple of years later, he got attracted by MIT, where he is still and now he is there as a Lester Wolfle full professor. Yeah, Vladan has received numerous prizes. Maybe to mention just a few of them, he has received the Sloan Fellowship, and he also is a fellow of the American Physical Society. So Vladan, we are very grateful that you are here today to give this MCQST colloquium on entangled optical atomic clocks. And we are particularly grateful because you had to squeeze in this colloquium also to within the on-site visit of the NSF for the CUA. Right? So I'm already very much looking forward to your colloquium today. And I also would like to encourage all the participants to ask questions during the talk. So I specifically asked Vladan whether this would be okay for him. And so I thought this would be nice maybe to have a lively and exciting discussion going on. Even in this, also in this colloquium. Yeah. Please, Vladan, the stage is yours.
Yeah, thank you very much, Michael. By all means, please interrupt me. It would be nice to have live questions. I'd rather be in person in Munich. I even heard you had first snow today, but you know, such are the times, and I'm very happy to be here virtually with you. So what I would like to tell you about today is an entangled optical atomic clock, how we generate and how we demonstrate operation of a state-of-the-art optical clock that uses entanglement between the atoms to enhance the performance. The main people here are postdocs Edwin Pedroso and Simone Colombo, who led this experiment. So I would like to remind you, or maybe briefly introduce you to the so-called standard quantum limit for atomic clocks and atom interferometers. This is just the question when you make quantum measurements on collections of independent particles, then because of the digital readout, the projection limit on the readout, you have a quantum noise even if you remove all classical noise from the system. And I would like to then show you how entanglement between distant atoms can overcome this quantum noise, can reduce this quantum noise, and also more importantly, how it can be generated between distant atoms that you would think as pretty much non-interacting over these large distances. And the way we achieve it is to put the whole ensemble inside an optical cavity and use photons as to mediate effective spin-spin interactions between the atoms, because the photons experience the collective state of all atoms. Then I would like to tell you how we do a particular form of entanglement that is called spin squeezing that I've introduced in the ground state of 171 ytterbium. This is our clock atom. This is one of the two standard high-performance optical transition clock atoms. And then how we spin squeeze on the optical clock transition in this system. So what is spin squeezing and how do we generate it? Well, first, you know, let me show you this graph that maybe you have seen before, just how clocks have improved over time. They follow their own Moore's law. The blue data points are here microwave clocks, and they have improved by about an order of magnitude or so per decade. In atomic fountains, etc. And then in red came this, you know, this newcomer. Starting here, you can see hydrogen experiments on here, and then ions, trapped ions, and trapped neutral atoms. And this newcomer has this much larger slope, so so far also exponential, you know, reaching levels at fraction uncertainty of 10 to minus 18. This is just mind-boggling. It's by far more than any other instrument that man has ever made. A fraction uncertainty this good. It means just that a clock, if it ran from all the way from the Big Bang until now, it would only be off by on the order of 10 seconds or so. So it's just an incredible uncertainty. So, what has enabled this, and how has this become possible? What is the new technology? And really relied on two technologies. One is previously to this time, it wasn't really possible to count frequencies. The blue are cesium microwave clocks that could be easily counted, but optical frequency cannot be counted. And so this is the big invention, that it became possible using frequency comb to synthesize optical frequencies and effectively count optical frequencies. And this is one of my favorite pictures here. I'm not sure whether it was taken in a Munich beer garden. It looks like it. Maybe Ted Hensch knows, but you see some here of the key players in this story. And of course, this was awarded the Nobel Prize in 2005. So this was one of the ingredients, the ability to count optical frequency. And the other very important ingredient goes back to Hidetoshi Katori and also Junier, who are holding the world record in the best atomic clocks. And this goes back to an idea that, for instance, to make these measurements, you cannot have just the atoms fly through your interaction region, through your laser beam, because the interaction time broadening would by far be the dominant broadening source for the experiment, but it's important to hold the atoms in place. And so Hidetoshi Katori, in a slightly different context, pointed out that if one had optical light traps that were tuned just right so that the light shifts in the ground state and the excited state would be exactly equal, these are now called magical wavelength traps, then it would be possible to perform precision spectroscopy on optical transitions without transit time broadening, basically with stationary atoms. Katori thought of this concept first in the context of quantum computing and how to make very good quantum bits, but it became actually a highly useful concept for precision measurements. So these are the so-called magic wavelength traps. And then the development of very, very stable lasers by Junier and other people, where now one can have coherence times of seconds or even tens of seconds on optical transitions. So how does an atomic clock work? An atomic clock really just is a quantum interferometer that measures the energy difference between two levels 1 and 2 via the quantum mechanical phase evolution rate. So if you prepare a superposition of two states 1 and 2, then we know, according to undergraduate quantum mechanics, that the phase evolves at a speed that is proportional to the energy and the time. And so basically, if you're able to measure this phase evolution speed, then if the energy is constant, it measures time. This applies not only to atomic clocks, but to many, many precision experiments. So if you want to measure some quantity and you make the energy proportional to the quantity, say the magnetic field or the electric field or any other quantity or the acceleration of the atom, then these atom interferometers can be used to perform high precision measurements of that quantity. In the context of measuring time and clocks, we would like the energy E actually not to depend ideally on anything, or to be as stable as possible, so that instead of measuring energy, we are really measuring here time. In any case, when you create the superposition and then you try to read out this phase, then because we know that quantum mechanical measurements are projection measurements, you have only an income atom is in state 1 or an atom is in state 2, and you get quantum noise. And that means that we have n atoms because of this quantum noise. So if you have 100 atoms on average, 50 atoms will be up, 50 atoms will be down, just like tossing coins. But in any given experiment, there will be a binomial distribution of outcomes. And so the noise will scale as the square root of n. So that means that in the end, atomic clocks scale as, or any interferometers of unentangled particles scale as 1 over square root of the atom number. So instead of thinking of tossing coins and the random outcomes of each individual coin, there's another nice picture to get the same physics in what we call a Bloch sphere. So what we do is we map this two-level system onto a spin 1/2 system. And then if we have n atoms, we just say, well, if all the atoms are doing the same thing, in any case, we can sum up all the spins of the individual atoms to define a collective ensemble spin. And if all the individual atoms are doing the same thing, if they're all aligned with one another, then this ensemble spin will be an large angular momentum whose magnitude is the atom number divided by 2, because each spin is a 1/2 system. So S is n/2. And then we know how to, how to think about quantum mechanical angular momentum. It's given by a vector, but this vector lives on the so-called Bloch sphere. We can rotate it, and it has discrete outcomes of, say, any z measurement. So in this Bloch sphere, Sz is the population difference between the two atomic levels, and states in the equatorial plane are equal superpositions of two states with a phase that depends on the direction of this plane. So what then is an atomic clock? Especially in the Ramsey sequence, we initialize the atoms, the spin vector down, meaning all the atoms in the lower state. We then drive a pi/2 pulse in the so-called Ramsey sequence to create an equal superposition of the states up and down, pointing in some direction. And then we let the state evolve. We let the state evolve, and in optical clocks, we let it evolve for many, many oscillations, maybe 10 to the 12 to 10 to the 15 oscillations or so. And we compare the rotation of this optical atomic system, of this optical Bloch vector, to our laser. And then we can use it to measure the laser phase relative to the atoms, or the laser phase of the atoms relative to the laser. So to measure this phase in the phase evolution, we perform a second pi/2 pulse around, say, the x-axis, the x-axis pointing towards you, and that converts this phase difference that we cannot directly measure into a population difference. And then the population difference can be measured. Now, what I've also shown here is quantum mechanically, the angular momentum has an uncertainty from the Heisenberg uncertainty rules, and this is indicated by this diffuse region. So it means that when you try to measure the direction of this Bloch vector, you cannot measure it perfectly because of quantum noise. You can only measure it with a certain resolution, which is given by the square root of n. So in this picture, the square root of n binomial noise from tossing coins from the projection noise is actually just the angular momentum uncertainty relations. How can we make the clocks better? Well, Heisenberg uncertainty tells you that the product of delta S, say delta Sy times delta Sz, if the vector is pointing along the x direction, is bounded by the length of Sx, but it doesn't tell you in principle that, it just means the area of this uncertainty is conserved. So this is this Fasin of angular momentum. This should be well known to everybody. This is the uncertainty product in the two different directions. So if you want to have a clock, you need Sx to be large, and so you have so that you can measure a direction well, and then you have this product delta Sy, delta Sc. But what you are allowed to do, and it would be perfectly fine with Heisenberg uncertainty relation, is to squeeze the noise in such a way that you reduce, say, the uncertainty along Sy, what would become the phase direction, at the expense of the uncertainty along Sc. And in that way, you can already kind of visually see that you can now measure phase better because you have lower uncertainty in that direction, or you can see it. How would you run a clock? Well, if you could prepare such a state that had this, reduced uncertainty in the phase direction, you would again run the clock in your normal Ramsey sequence as before. And then you can see that in the final pi/2 pulse, this reduced uncertainty in the phase direction gets mapped onto uncertainty in Sc. And basically you get smaller fluctuations in the atom number measured in the down and up states than before. It is clear that this requires entanglement because this is a lower noise than you would get from throwing all coins individually from the projection noise. So this is a many-body entangled state that is required to generate this kind of improvement. And this is what goes under the name of spin squeezing or spin noise squeezing. This redistribution of quantum noise from one quadrature, the phase quadrature that you are directly measuring, that matters to the other direction. So this has been known for a long time, over 20 years, but people really didn't know how to generate it. Theoretically, it's easy to write down, and it was first done by Kitagawa and Ueda. And the Hamiltonian is easy to write down. One way to think about it is to say, well, what's the simplest Hamiltonian in spin space? It's maybe Sz. What does Sz do? Well, it simply generates rotations about the z-axis. So the Hamiltonian Sc just generates, when applied by a certain time, just rotates the state by a certain amount about the z-axis. If I wrote down Hamiltonian Sc squared, then you can think of it that's a rotation about an Sc axis, but with an angle, a rotation angle that is proportional to Sc. So basically that means that a state above the equator rotates a little bit faster and the state below the equator rotates a little bit slower. And so basically the SZ squared Hamiltonian is the simplest Hamiltonian that will generate the squeeze state. This was pointed out by Kitagawa and Ueda. Their paper was turned out by PRL as being not very relevant, I guess, at the time. And also they wrote in the paper, we can write out that Hamiltonian, but we really don't know how to entangle 1,000 atoms or a million atoms to generate this Hamiltonian. So we found a way to generate this Hamiltonian using light in a cavity. I'll show you a simple example here that we did already now almost a decade ago, where we used as two clock levels, two hyperfine levels in terbium. States 1 and 2 were two hyperfine states. We placed the atoms inside a cavity and we just shone light onto the cavity. So here shown is the cavity resonance as a function of frequency, and we parked the laser on the slope of the cavity resonance. And the light tuning was chosen in such a way that if an atom was in the lower hyperfine state 1, it would see red detuned light by a certain amount, and if it was in the upper hyperfine state 2, it would see blue detuned light relative to an atomic transition where these two detunings were equal. So basically atoms in the state 1 constitute an index of refraction larger than 1, like a piece of glass, and atoms in state 2 constitute an index of refraction smaller than 1. And if you have exactly equal atom numbers in the state 1 and 2, then these index of refraction effects just cancel, and the cavity is exactly at the position where it used to be when it was empty. However, if you have quantum fluctuations, so basically if you have a state at the equator, exactly equal atom numbers in 1 and 2, then the cavity is not affected. However, if you have quantum fluctuations, if you have more atoms, say in the up state than the down state, you live up here, then you have more atoms, say in the clock state, and the cavity will be shifted one way. So what that means is that if the cavity, say you're up here, the cavity is shifted one way, say closer to resonance, this means more light will enter the cavity. And what does the light do? Well, the light is blue detuned relative to one transition and red detuned relative to the other transition, so it produces a differential light shift between the two clock levels. So the fact that more light enters the cavity means that there will be more phase evolution relative to the equator due to the light shift for this point up here. So this point, say, will move to the right. Similarly, if you have a quantum fluctuations where you're down here and you have more atoms in the lower hyperfine state, then less light will enter the cavity because the cavity will be tuned by the quantum noise of the atoms the other way. And therefore, you have less light in the cavity, less differential light shift, and this point will move relative to the equator in the other direction. And you can kind of pictorially see that this will produce a squeeze state. So basically, how do you think about this? These atoms are far away from one another. What happens is the quantum noise of the atoms gets mapped onto the light field, and then the light field acts back onto the atoms, and that produces in the end the entanglement or the correlations between the SZ spin of the atoms and the SY spin of the atoms, or produces the squeezing. So formally speaking, we have an interaction Hamiltonian here that has three terms. The first term here is just the energy of the photons inside the cavity. So C dagger is here the creation operator for photons inside the cavity. We have a cavity resonance frequency. So this is just the energy for n photons inside the cavity. We have also an atomic energy. This is the atomic energy difference. SC is just the population difference between the two states. So this is just the energy of the atoms alone inside, the atoms alone, depending on SC. And then formally the interaction term is a cross term that takes the form C dagger C, photon number inside the cavity times SC. And you can think of this interaction term in two different ways. You can say, well, either I group it with the atomic resonance frequency, so I can write the sum of these two terms this way. So what is in this case happening? Well, if I have n photons inside a cavity, there will be a differential light shift on the atom, so the atomic resonance frequency will be shifted by a little bit. Excuse me. So that's kind of a differential light shift per photon, or you can group it with this term over here, and then you can say, well, if I have a population imbalance in the cavity, SC, as described by SC, then this will tune the cavity resonance. So the cavity resonance will no longer be omega C. It will be shifted by some small amount due to the atoms. And then that shifts the energy of the photons. And how does this give rise to an effective SE Hamiltonian? If you parked on the cavity resonance, then this photon number inside the cavity C dagger C is proportional to SE to lowest order. So you can think of it alphabetically eliminating it. So the C dagger C operator becomes effectively like an SE operator. And so this term produces an SE squared as required by Kitagawa and Ueda for spin squeezing. So using the system, back in 2010 already, we could demonstrate with a rather poor clock, because it was a microwave clock, that the coherent state, this is showing the imprecision of the clock as a function of averaging time. And this is the black data points are a coherent state clock with unentangled atoms. This is the so-called standard quantum limit. So this is the best that you could do with unentangled atoms. And then we could show that if you used a squeeze state, we could be a few dB below this below this level for unentangled atoms. However, as you see, the precision of this clock was not very good at the time. It was in the range 10 to the minus 9, 10 to the minus 10, and that was mainly because we were using a microwave transition clock, and it wasn't a magic wavelength either. So there were light shifts on the trapped atoms that limited the precision of this clock, and then this noise over here is magnetic field noise as well. So it was also magnetic field sensitive. So it was a proof of principle experiment, but not really usable as a clock. Since then, people have really pushed this. There have been beautiful experiments in various groups. People used atomic collisions, state-dependent collisions in Bose-Einstein condensates to make effectively a spin-squeezing Hamiltonian or similar Hamiltonians. There were many groups. Markus Oberthaler's group did beautiful experiments. Philipp Treutlein, Mike Chapman, Carsten Klemmt, Jörg Schmidmeier, etc. So there's been a number of experiments in condensates. We don't like this approach very much for precision experiments, because the fact that you're using collisions also means that when you're doing the clock or the precision measurements, these collisions might affect you. It's hard to turn off these collisions in a dense atomic gas in a Bose-Einstein condensate. We use rather low density distributions of atoms. And then there has been another group of experiment led by Eugene Polsik and more recently also by James Thompson and Mark Kasevich, which uses light, either the way we do it or simply by a weak measurement that I haven't introduced, but it's very closely related to this, to do spin squeezing. And the current record is close to 18 dB or close to 20 dB actually, in experiments from a few years ago by Mark Kasevich and James Thompson. So the measured spin squeezing is 18 dB. The inferred spin squeezing, because this is limited by measurement resolution, is as much as 20 dB. So one can get a huge factor potentially of spin noise reduction. 20 dB means a factor 100 invariance under the quantum, under projection noise, which potentially could mean the same number in integration time if you could use the full thing. So but all of these experiments were proof of principle experiments that were not really done in any real clock. So we set out to do experiments on a real optical transition clock. Maybe this is a good moment to pause and just to see whether there are questions.
Hello, I have one.
Mm-hmm.
Okay, thank you very much for the nice talk so far. I just wanted to ask you, so one motivation for this squeezing was basically to reduce the uncertainty in the number, say in the imbalance that is in the Z component on the Bloch sphere. And then these shear forces which are distorting the ensemble on the, say, on the east pole, are kind of making the ensemble in the diagonal, if you want, right?
Mm-hmm.
But then, is this reducing the uncertainty in the Z direction? Or is it just reducing it along some diagonal direction?
Very good. So you're right. This spin squeezing Hamiltonian that also Kitagawa and Ueda used does not reduce the noise in the SC direction. It reduces the noise along some other axis. Very good observation. But we are able with pulses to rotate the state any way we want, as long as we know along which direction the state is squeezed. So I will show you that. So when we do these experiments, we actually rotate the state by variables amounts, and then we measure the variance. It's a very good observation, and then it's squeezed around along the right direction.
So there is like a third pulse, basically.
Yes, there's like a third pulse. Mm-hmm.
Okay, thank you.
Are there other questions? Right, so the spin squeezing or so-called one-axis twisting Hamiltonian really reduces the noise in one direction. Okay, so we set out to do this now in real optical transition clock atom, and there are two neutral atoms that use neutral atom clocks that use large atom number. One of them is strontium, the other system is ytterbium. So the system we work with is ytterbium. It has it's a 2-electron atom that, however, can still be laser cooled, and we chose 171 ytterbium that has a nuclear spin 1/2. So in this ground state is spin 0. So there's no electron spin degeneracy, but there's two degenerate states of nuclear spin, -1/2 and 1/2. And then there are 3 different transitions: a strong transition in the blue near UV, which can be used for laser cooling, intermediate strength transition. So this one has like a 20 megahertz line with intermediate strength transition that has 180 kilohertz line width in the green that we use for spin squeezing. And then there's this clock transition in the yellow that has a line with at the tens of millihertz level, so a very long lived data. This is where we do the spectroscopy ultimately. So we are using this green light to create spin squeezing in this transition between these 2 states, as I will explain to you in a moment. And then the idea is that once we will use spin squeezing to create squeezing between the 2 nuclear ground states, like so, indicated like so, on this Bloch sphere. And then what we'll do to get a squeezed optical clock is we will do a high fidelity pi pulse to transfer one of these states up to the clock state. And if you do this all phase coherently and well controlled, then you can maintain all the quantum coherence properties that you had in the ground state now on between these 2 states, and you can run a squeezed clock. So that's the idea. The experiment looks like this. We need a high quality cavity in this system, and to be able to make even higher quality than we actually need for spin squeezing, but it will allow us to do other experiments. We use an asymmetric cavity with a so-called super mirror, or so-called super mirrors. One of them is the commercial big super mirror with a radius of curvature of 2.5 centimeters, and the other here is 150 micrometers radius super mirror that we made with a method that was introduced by Jakob Reichel first. So we can make a cavity that has a finesse of something like 20,000, meaning about a few thousand round trips of a photon inside the cavity before it is lost. And the nice property of this cavity is that it has a very small mode waste. So basically, by placing the ensemble at different locations in this cavity, we can change the coupling between the atoms in the cavity between some moderate values to some very high values over here. We then run a magneto-optical trap. For the experts, it's a mirror magneto-optical trap that creates a little ensemble of ytterbium atoms here, maybe 100,000 ytterbium atoms or so, a fraction of which we can then trap into this trap. The light field inside the cavity has 2 colors. One is a trap color. This is the so-called magic wavelength trap. So there's a particular wavelength that recreates exactly equal light shifts between the ground and excited state. This is known from other clock experiments with ytterbium. So we choose that color. It forms a standing wave where we trap the atoms. And then we also use the cavity for spin squeezing by sending in light from below that will create this entanglement between the atoms. So this is the picture of the setup. As I said, this is the magical wavelength trap. So it has this feature that the ground and excited state have exactly the same polarizability at this wavelength and therefore experience exactly the same light shift. And then as to the spin squeezing, what we do is we first apply a magnetic field that splits out this upper excited state that has an electromagnetic moment by something like 20 megahertz between these individual levels, so that we can identify a single closed 2-level transition between this nuclear state plus 1/2 and this state of total spin 3/2. And if we park the cavity on resonance and place a number of atoms in the state, then what happens is the cavity mode and the atomic mode get coupled with another, and this leads to this hybridization or vacuum, so-called vacuum Rabi splitting. So what were 2 separate modes, when they're coupled to one another, leads to this double structure of 2 modes, which are joint modes of the cavity and of the atoms. So in frequency space, they look like this. They're sometimes called vacuum Rabi peaks, these two split peaks. And what we need to know is that the splitting between these peaks is some frequent number in frequency units, the so-called single photon Rabi frequency times the square root of the atom number. So basically the splitting between these peaks depends on the atom number in this state. So if we create a superposition of these two nuclear ground states, plus minus 1/2, then by measuring the splitting, we can measure, say, the quantum noise of the atoms in this state. So the way we do it is we park a laser incident onto the cavity, and then for measuring the atom number, we just sweep the laser across the two resonances and measure the splitting precisely by counting the transmitted photons. And that gives us a measurement of the atom number. To measure spin squeezing and to not be limited by projection noise, you need to be able to measure better than the projection noise. What can we do? Well, first of all, to measure SZ, really, we make one measurement. We then do a pi pulse where we swap these two populations, and then we do a second measurement, and then the difference between these two measurements is the spin vector SZ. So when we do this kind of measurement, how well can we do? This is now shown on a logarithmic axis, how many photons we send into the cavity. And here's how well we do. The blue line is the so-called standard quantum limit. So this is the shot noise of the atoms. So for us, typically, it would be 1,000 to 10,000 atoms. So this would be maybe 100 atoms resolution. And then how well can we do? Well, if we have few photons, then we are limited by photon shot noise. We don't know where the cavity resonances exactly are. And the more photons we send in, the better we get. So we measure better and better, but at some point the system again turns around and our measurement resolution becomes worse. Why is that? Well, we are shining this light into the cavity, but off resonantly by 20 megahertz or so. It also couples to this state, and so there's also what we call Raman scattering. There's basically a population transfer of atoms from this state to that state, and that also leads to quantum noise. And this extra population transfer is responsible for this turnaround. So at the moment, this limit set by Raman scattering, we can measure about 10 dB or a factor 10 below the standard quantum limit. Okay, so this is how we measure SZ to quantify spin squeezing. How do we spin squeeze? Well, pretty much in almost the same way. All that we do is we now park a laser on the slope of the cavity resonance, like I showed you before. And again, now quantum noise between the atoms will shift the cavity resonance one way or the other way, which will lead to more or less a light shift between the atoms. So in one case, let's say the laser is parked here. If the population difference is the same, we get a certain amount of a light shift between the atoms and phase shift. If the cavity is moved one way, less laser intensity, we get less phase shift. In the other case, we get more phase shift. So again, we realize this effective SZ squared Hamiltonian that leads to basically this single axis spin squeezing just as before. However, there's one caveat here. The Hamiltonian that we wrote down is not really SZ squared, is this SZ times C dagger C, the photon number inside a cavity. What this means physically is that you could have measured the transmitted light, for instance, through the cavity and gained information about the atomic state. And since we cannot measure this, so basically it means the light and the atoms become entangled. Beside the atom-atom entanglement, we have also light-atom entanglement. And since we cannot measure the light perfectly for various reasons, we lose information about the atomic state, so which will generally lead to non-unitary evolution. So it will generally broaden the state. So however, it turns out that if we vary the detuning, it turns out that the spin squeezing shown here in red falls off more slowly with light atom detuning than the light atom entanglement. So the light atom entanglement is kind of a higher order process. So it turns out that by reducing the spin squeezing by a little bit, by going off resonance, we can reduce the light atom entanglement a lot. So if you're out here in this region, the light really acts as a catalyst, which is very interesting. It comes in as a coherent state of light. It creates the spin squeezing between the atoms, and then it comes back out nearly as a coherent state of light, containing almost no information about the atomic system. This is what allows us to have an effectively nearly unitary or Hamiltonian evolution of the atoms. So we do that as well. And then we presumably have the spin squeeze state. How do we measure it? Well, this comes back to your question that you asked before. So we have this normalized variance when we don't rotate the state at some level. And then what we do is we rotate the state and then perform a measurement. So this is the standard quantum limit. So what we do is we rotate the state a little bit. You see the noise is reduced. And then when we rotate the state more, the noise increases again. And then when we have the what we call the anti-squeezed axis along the vertical direction, we have a lot more noise than the standard quantum limit. So basically we determine the angle alpha where we have the reduced variance, and this is the direction of our spin squeezing. So how well can we do? This shows in a plot the normalized variance versus this rotation angle. It's shown on a logarithmic plot because these rotation angles that are relevant are quite small. On a linear plot, it will be just an ellipse. So we have an unsqueezed state, and the noise is at the standard quantum limit and doesn't depend on rotation angle. And then with increasing squeezing from green to red, we get more and more squeezing, and at some point we hit the detection limit. So actually the spin squeeze state that we make is better than what we see. We just cannot measure it anymore below this 10 dB limit. And we concluded it was around 15 dB spin squeezed, also if we could have measured it. So we can then plot as a function of this shearing strength of how strongly we deform the state. This is plotted on the horizontal axis. We can predict how well we can do. So the red curve is the inferred spin squeezing of about 15 or 16 dB. But we cannot use the full spin squeezing because it turns out that scattering processes also shorten the Bloch vector and shorten a little bit the contrast of our measurement. So when we combine everything, we get these green or blue data points. So we could improve the clock by 6 to 8 dB at the moment with this kind of system. And this has to do, as I said, with the contrast of the clock. So what happens is the Bloch sphere is also shrinking. And so if you're reducing noise, you pay a little bit of a price by shrinking the Bloch sphere, and there's an optimum of shearing and squeezing. Nonetheless, we could do better than the standard quantum limit. So here comes the most recent and final step where we transfer the spin squeezing to the optical transition. So basically, we have now created the spin squeeze state between the ground states down here. And now we need a high performance pi pulse to transfer the state up here. How well do we need to do? Well, if you had a 99% performance pi pulse, then you would leave 1% of the atoms in the remaining here in this state, and the corresponding projection noise or quantum noise would then be 20 dB. So basically, if we want to have, say, 10 dB of spin squeezing, then we have to transfer well better than 90 or maybe 95% of the atoms in a pi pulse while maintaining phase coherence. So how do we do this? It turns out that because of the Doppler effect, so we had the atoms trapped in an optical lattice in the vertical direction, but we have to apply the clock laser from the side because we like a running wave clock laser. So the Doppler effect in this direction would lead to too much broadening. So we apply a second lattice along the clock laser direction to be in the so-called Lamb decay regime, where the atoms can absorb a photon from the clock laser without recoil or by giving the recoil to the lattice. So we are now in a 2D lattice and we apply the clock laser along this direction, and then we measure the atoms through the cavity. We can see sidebands, motional sidebands, and also this is just the Rabi scan of the sidebands. So we can, after various improvements, we could reach about 90 to 95% efficiency by cooling the atoms. For that, we had to cool the atoms so that most of them were actually in the vibration ground state of the system. We did a new version of Raman sideband cooling to 3 microkelvins so that more than 90% of the atoms are in the ground state of the system. And under this system, we can then do Rabi flopping on the clock transition, and we see some fairly nice Rabi oscillation where this transfer efficiency is around 95% or so for a single pi pulse. So we see good contracts of the Rabi oscillations. And so now we are ready to basically, this was done with an unentangled state, to do it with an entangled state. So to verify whether we are doing well enough, what we do here is I'm showing now 2 different Bloch spheres. So this pink, not this violet Bloch sphere, you can think of this as the Bloch sphere corresponding to the 2 nuclear ground states shown down here. So this is basically the spin space of these 2 nuclear states. And then after the optical transition, we live on a different Bloch sphere, which is the Bloch sphere between 1 ground state and 1 optically excited state. So this is a Bloch sphere at optical frequencies. On the optical transitions is shown in yellow. So basically we spin squeeze the state in the ground state. Then we transfer it with a pi pulse onto the optical transition. And then for really running the clock, we will let it evolve for Ramsey evolution time. And then for the measurement of the spin squeezing, we'll transfer back to the ground state, and then we'll do our final measurement. And so basically, if the atoms were decohered, if the spin squeeze was destroyed on this optical transition, then we wouldn't expect to see a spin squeeze state after we return back. So we create everything in the ground state, we map onto the excited state, we go back to the ground state for our final measurements. This is how we do things. And so this is now showing you the normalized variance as a function of angle as before. We rotate the state, we measure the variance as before. You see we start at the standard quantum limit because the initial state has no reduced noise along SC. If we rotate by just about the right amount, 10 degrees, we get this reduced noise. And then when we rotate too much or make it all vertical, we get this anti-squeezing. And the two colors correspond, in one case, the violet colors correspond to just measuring the state directly before doing the pipe, without doing the pipe pulses. And the yellow data points correspond to placing the state on the optical transition in the upper electronic state and then bringing it back down. Rather quickly, not really performing a long-time Ramsey sequence just to see the quality. And so you can see that the yellow data points and the violet data points really agree with one another. We don't see any significant deterioration of our spin squeeze state from this transfer, and we don't really expect it because here we have, something like 6 dB of spin squeezing, and we have more than 95% fidelity of the transfer on the Raman pipe pulse. And so this, leads us to conclude that we can map the spin squeezing onto the clock state and back without deterioration. So how well can we do? So first we measure it as a function of holding time, but we orient the spin squeeze state in the upper state horizontally. So we're not really measuring time or phase. We just want to see how well the state lives if it's squeezed in the SE direction. So the blue data points show the coherent state. This is a logarithmic scale. So our clock laser is not very good at the moment. We locked it to a very ultra-stable cavity, but it's not as good as the best state-of-the-art optical clock. So we have only coherence times of a few 10 milliseconds at the moment. And so this is responsible for the increase of the coherent state. And then we can do the same thing with the spin squeeze state down here, shown in red. And then eventually it also increases because of the phase. This state is not really measuring time because it has this large uncertainty in the phase direction. In fact, this state is rather robust relative to phase noise. So our main noise here is phase noise. In any case, the system behaves just as we expect, and the spin squeezing is maintained. So as a final experiment now, we go really to this sequence and we rotate the state with this pipe pulse so that the reduced axis, the reduced noise is in the phase direction like so, and then we do a Ramsey measurement. And so what we see in this system is basically, this is now showing the Allen deviation as a function of averaging time. The blue data points are for a coherent state, for an unentangled state. The red data points are for a spin squeeze state for the full sequence. So this is this full sequence where we spin squeeze, we map onto the optical transition, we do a pi pulse, we do the Ramsey sequence on the optical transition, we map back onto the ground state and measure. And so we can do at the moment about 4 dB better than the standard quantum limit, and about 5 to 6 dB better than the coherent state, which also suffers from contrast noise reduction. So at the moment, we are not fully within the standard quantum limit. That's because our clock laser is not very good. So in blue is shown the noise from the standard quantum limit, the quantum noise, and in yellow is shown the extra phase noise of the laser. And so we see that we can operate inside the region, which is lower than the total phase noise due to the entanglement. But in the future, we really need to get and want to get much, much lower. So the plan, we are already working on improving the clock laser. So currently our coherence time, it's limited by the coherence time of the laser, has nothing to do with the atoms, we believe. We're pretty sure about that. So we're working on improving the laser coherence time from our current value of around 10 milliseconds. Better, state-of-the-art experiments have more like seconds coherence time. And that's what bring this clock back down. So right now we are kind of at a 10 to minus 13 level or so in a few seconds. The integration time, the best clocks are at a 10 to the minus 15, slightly below 10 to the minus 15 level. And this is simply a function of coherence time. So this was done with a very short Ramsey time of only 170 microseconds. And so the next experiments with improved laser that we haven't done yet will be hopefully to increase this Ramsey time by 2 orders of magnitude or so to be much deeper in this regime. How well could you do? Well, we estimate that with just 1 second of integration time, one could, with a spin squeeze clock, be already at the level of something like 10 to the minus 17 fractional uncertainty or better, which would then enable to very quickly to average down to look at various effects. So what would we like to do next? This brings me to the end of my talk. We want to improve squeezing, improve laser stability. We're working already on that. And we hope to be able to directly, with multiple clocks, for instance, measure gravitational edge shifts of, on small scale, maybe a centimeter or so within our cavity in a few minutes. There's also a very interesting different direction, which I haven't had time to talk about. There's interesting tests that you can do about new forces and dark matter if you can measure different isotopes very precisely. And the terbium has many different isotopes that can be measured. So we also plan to do precision isotope shift of the clock transitions for dark matter searches. So this is the end of my talk, and I thank you for your attention.
Yeah, from my side. Thank you very much for this very nice and clear talk. So what are the questions by the audience?
I actually have a question. So you mentioned that part of the limitation of your setup is that you cannot measure the squeeze state better than your measurement precision just given by the Raman scattering. So at what point do you think, is this already a limit? Or at what point when you improve laser coherence will this be the limit? And do you have an idea on how to get around that, basically?
We know how to get around it. So this Raman scattering, basically that these atoms see the same light. There are two ways to do it. One way would be just to increase the splitting here in the excited state and reduce the Raman scattering with larger magnetic field. However, what we will do instead, now that we have these pi pulses, and that would make it fractionally better, what we will do is we'll take this population of a pi pulse and hide it in the clock state. So instead of using these two levels in the future, we will just do as we do now for the Ramsey sequence, but we'll do it for the whole thing. Instead of working between these two levels, this level will be replaced by the clock state up here. In which this case the Raman scattering should be completely gone, and we should be able to get much better measurement resolution. And we estimate that with that, we should be easily able to reach 20 dB or so of measurement resolution, mainly limited then by how well we can do the pi pulse on this transition, which at the moment we can do with 95, 96%, but we think we can push it to maybe 99% or so. So that's why we think we can bring this level down by another 10 dB. Very good question.
One question in the same direction, so maybe in a similar direction. What about collisions when you go to longer times in the present setup? So I mean, you say you can just increase laser, make better lasers, you go to seconds, coherence times, then of course collisions will start to matter here.
Right. So what we'll do is, if once collisions matter, we are still relatively far away, but at some point they will matter. We will just introduce a laser beam along the third direction and go to 3D lattices. That is also the direction, say, that Juliet is going. So all the state-of-the-art atomic clocks are, not all, but the new direction is to go to 3D lattices. So basically, we'll just add. Where's the picture here? We'll just add a third standing wave along the third direction and just do things in a 3D lattice. We are also looking at direct laser cooling. This terbium is a fermionic system. We think we can directly laser cool it with methods that we have demonstrated for BECs, closer to basically increase the filling fraction closer to Fermi degeneracy, but then load it in a 3D lattice.
Vladan, very good.
Oh, thank you.
Can I ask a question? I think towards the end of your talk, you showed a plot where you have the lifetime of the squeezing. Exactly, exactly this one. So it's 100 milliseconds or 1 second, depending on where you look and how you look. What determines this lifetime?
This is at the moment purely phase noise of the laser.
Mm.
So, this is what we're measuring is always, the lifetime between the atomic state and the laser phase, right? And so at the moment, it's completely limited by the laser. At the level of a few seconds, it will be limited by scattering of light from the trapping light at the current intensity, and we see that the lifetime gets longer. Just a single atom lifetime gets longer when we reduce the laser intensity. But at the moment, it's just the quality of the laser that limits everything.
How big is the tuning between your trap laser and the atoms?
It's a few hundred nanometers. So the magic wavelength is 776 nanometers, and the transitions are at 400 nanometers and 556 nanometers. Currently, the scattering time is about 10 seconds in the typical magic wavelength traps that we use. And Junier sees a similar problem in strontium, where also the scattering from the laser limits the lifetime. And then when he reduces the trap intensity too much, then he has tunneling in this 3D lattice, for instance, and then he has collisions again. So there's a little bit of a compromise there.
So what kind of perspective do you see then if you want to go to measurement times of 1,000 seconds or whatever, having a really good clock over a long time? I think you want to eliminate the scattering.
I think if you want 1,000 seconds, we will both need to switch to a new atom. So kind of 100 seconds is maybe still reachable. It looks like, and that's where I see the field going. Once this is pushed to, there's also a natural lifetime limit, right, which is also on the order of 100 seconds or a few hundred seconds or so in strontium. So the way I see this will be pushed to the natural lifetime limit. Also the vacuum limit, maybe, right? The clock lasers. June has this. You may know he has this. Cryogenic cavity which can keep the coherence time for 4,000 seconds or so. I think eventually, when we want to go beyond 10 to minus 19, 10 to minus 20, we'll need atoms with longer lifetimes. And a few have been theoretically identified. For instance, the terbium is supposed to have another clock transition, and so on. But I think we want a different transition ultimately.
But what I meant is you also have to reduce the scattering from the trapping, no? From optical trap.
Right.
No?
Exactly, which means you're right. You need also a magic wavelength that is far enough away.
That's what I have in mind. Yeah.
Exactly. So so the natural limit for both ytterbium and strontium, the best clocks at the moment, lies somewhere, I would say, between 100 and 1,000 seconds of Ramsey time, right? And then you can't reduce the trap anymore, I think.
Thank you.
Thank you for the question.
Speculative question from my side: would it be also possible to form a network of clocks essentially with this to further improve the accuracy?
Yes, it would be. You can entangle both distant ensembles inside a cavity. So we are thinking of some of the next experiment will be multi-ensemble experiments, where we will entangle, using the light, you can entangle also the ensembles with one another, but then measure relative to one another. And so entangled networks can improve things. You could also think of doing this at a distance, and it becomes more interesting, but that's one direction.
So the idea would be that you take an array of cavities, then the entangling pulse would be along the line of cavities, essentially, something?
Yeah, you could use the light as a communicator between the cavities, but that requires you not to lose much photons in between, so that you can keep the evolution. So at some level that's possible, I would say. At the 10 dB level, you could entangle different ensembles via fibers between them. We will try experiments within a cavity. There you don't have the limitation from atom loss, and there you can do much better. And then you can do some kind of differential measurements. Should be very, very good. And that's why we're thinking of gravity and other experiments. But yes, I think one exciting long-term prospect is to think how to entangle distant clocks with one another.
Thanks. Further questions?
But then the Raman scattering was, maybe listen careful enough to what Johannes was asking. The Raman scattering is limited by the detuning to the Zeeman state, or so could you go to larger Zeeman splittings to suppress that more, to increase the performance of the squeezing?
We could do, but what we really do is we'll take a pi pulse here and we'll map the state onto the clock state. So we won't leave the atoms in the other hyperfine level, in the other magnetic sublevel. We'll actually basically replace this state by that state. You know, once we have good enough pi pulses, which we have now, then we can do that. And then we have no Raman scattering whatsoever.
But in those states, you do the squeezing preparation, or no? That's after you did the squeezing.
So no. So basically, let's see what I have. So if you imagine this was not spin squeeze. So right now we apply the light here on this transition and spin squeeze. So maybe we can go to this picture here. So right now we apply the light on this transition and spin squeeze, but the atoms are in this other state and Raman scatter. But before we spin squeeze, we hide the atoms in the clock state. We apply the light, then we do a pi pulse on the clock state, we apply the light again. So we can map these atoms coherently onto the clock state, and then they're completely out of the picture.
Take them out of the picture, basically, that they just become spectators at that point. But then you probably just have polarization, impurity, Raman scattering. No? If you're not sigma plus on that transition, then you have a little bit of sigma minus.
But that's another 20 dB down, right? Because that's, you're right, but that's filtered by polarization. A lot, and that's also, we don't have a pi component. It's this other sigma minus component. That's another 40 megahertz away. Yeah, you're right. That will be another limit. It's very small.
So then, by numbers, in terms of numbers, how much do you improve the spin squeezing by this hiding shelving method to improve?
I think it will be limited by the quality of the pi pulse on the optical transition. Right. So basically, for 20 dB, we need 99%. At the moment, we're at 96, 97%.
And that's limited by laser noise again, right now, the pi pulse?
Yeah, it's limited by the phase noise of the laser. It's the same clock laser that we use. And it's basically when we improve the laser, we think we can do much better. So everything at the moment we think is due to our laser, which is not as well locked to the cavity as the best experiments.
So there could be still time for maybe one more question.
I would have a question. So is it important that the atomic cloud is at the very center of the cavity? So is it a problem if the different atoms have a different coupling to the cavity?
It's a very good question. So it's not really important. So if the atoms have different couplings to the cavity, you just get to renormalize the spin. It turns out that you can still describe it by a spin model. You just shorten the effective spin length factor a little bit. However, what we find happens is while we laser cool, because of the way we do laser cooling, the atoms we optically pump via the cavity, the atoms actually migrate all to the positions with the largest coupling. So we find that the coupling is rather uniform. So we would expect distribution of couplings exactly because the cavity, the wavelength of the trapping light is different from the wavelength of the squeezing light and the probing light. But we find that when we do it right, the atoms actually migrate, and we have within a few % or so homogeneous coupling between the atoms. So that just renormalizes the Bloch sphere. Essentially, it's not important. It would only be a limit if you could squeeze all the way to a Dickey state, right? So if you squeeze more and more, so that you're kind of wrapping around the Bloch sphere, if you could resolve the individual SZ levels, at that point, the variation in coupling would matter. But we are not there yet. I should also like to point out, I don't have a transparency here, but that we are actually on a scale between the standard quantum limit and the Heisenberg limit. We are in our newest experiments more than halfway towards the Heisenberg limit in experiments that I haven't shown yet. So, at some point when you're near the Heisenberg limit, then this coupling will become important.
Yeah, excellent. Good. So I think we had a very lively discussion and really a great talk. Yeah, thanks again for being here today and for sharing your time with us. And I think with that, we can close this colloquium. And I think, Vladan, so today you are busy with the on-site visit, but tomorrow I think there are still a couple of discussions with locals. So thanks again for taking this time.
I look forward to that, and also look forward to one day seeing you all again live.
Yeah, right. So we're back to normal mode. We certainly should have you here in person.
Thank you very much once again.
Yeah, thanks a lot. All right, bye.